most notion in algebraic coding theory is the code equivalence. So what happens when we transform the given linear code to other one with spatial transformation, or we see that two codes are equivalent if there exists a vector whose coordinates are non-zero elements from finite field FQ, such that each code word from C2 can be obtained as a multiplication by A from a code word C1. So by this multiplication, what we mean is that it's star multiplication. So that means we multiply these coordinates of given vector A by the coordinates of the vectors or the coordinates of the code words from C1. So in that, here it can be a nice exercise. In that we can see that the generator matrix of G1 or the generator matrix of G2 can be obtained by the multiplication of what are called permutation, or more generally monomial matrices. So this permutation, or let me first define the permutation matrix. Permutation matrix is going to be square matrix, in this case going to be n by n, which contains only one non-zero, indeed only one entries at each column and each row. So for instance, in 3 by 3 case, 1 0 1 1 0 0 0 0 1 is a sample of a permutation matrix, because when we check the columns and the coordinates, we only come across only one entries, which is 1. And more generally, for we can define what is called monomial matrices. In this case, they are going to contain these non-zero entries, but they are not supposed to be. They are not going to be necessarily 1. So that means at each entries, for instance, let me consider a matrix whose entries from F3, which is 3 by 3, and in this case, this is going to be monomial matrix. And indeed, you may also observe that the monomial matrix can be written as a multiplication of a permutation matrix times a diagonal matrix, probably with entries 2, 1, and 1. Please check it. Indeed, this definition, or this definition, this definition can be seen as multiplication. So this is why I wanted to mention spatial transformations. Let me write this part more clearly. If you consider the permutation matrix, equivalence means that there exists permutation matrix P such that G1, the generator matrix of C2, is a multiplication of the generator matrix of C1 and P, and in this case we say monomially equivalent if there exists a monomial matrix such that the generator of C2 is multiplication of generator of C1 and P, C1 and M, sorry. And here M is going to be multiplication of some permutation matrix and the diagonal matrix, which has non-zero entries on the diagonal. And indeed, thanks to this definition, or thanks to these facts, we can see that the equivalent codes have the same dimension and have the same minimum distance, because this multiplication by the non-zero coordinate doesn't change the minimum distance, or if we change the if we apply permutations on the coordinates, so again weight doesn't change. But we have some counterexamples which have the same dimension and the same minimum distance, but they are not equivalent. Moreover, equivalent, even though it preserves the dimension and the minimum distance, it doesn't preserve all interesting properties like automorphism groups that I will try to explain at the end of this lecture. So equivalence does not imply that they are supposed to be the same automorphism group. I only give the definition of the automorphism group, but it can be checked from the literature, some counterexamples. But for the moment, what I want to see that we can indeed understand the equivalence of algebraic geometric codes by considering the equivalence of the divisors. Indeed, proposition 2 to 14 will be an answer for this. So let me consider two divisors G1 and G2, which are equivalent to each other, and they have disjoint supports by given D. I follow the same notation in the beginning of the lecture. So D is the sum of the given n distinct places, PIs, and support of G, intersection support of D is an empty set. Then we will see that if we consider algebraic geometric codes, which are defined in terms of these two equivalent divisors, G1 and G2, we produce equivalent codes. And conversely, if a linear code C is equivalent to an algebraic geometric code, which is denoted by CL of D and G for given D and G, then we can see the existence of a divisor G prime, which is equivalent to G, has different support from the support of D, so that it has no zeros at given distinct places, rational places PIs. And indeed, this code is nothing but the algebraic geometric code, which is defined by G prime. In order to prove part A, so we know that by the assumption G1 and G2 are equivalent. So by the definition of the equivalence of divisors, we know the existence of an algebra function, which allows us to write G1 as G1 minus Z. And the support of G2 is disjoint from the support of D, so that means Z cannot have any poles or zeros at Pi. Z has no zeros and poles at Pi's. And indeed, this shows us valuation of Z at Pi's are zero integers, and equivalent, indeed we can see that evaluation of Z at Pi's are non-zero constants. And indeed, if we consider the vector whose coordinates are the Z of Pi's, we get a vector in FQ star n, so each coordinates are non-zero. And on the other hand, because of this equivalence, on the other hand, by the assumption, because of this equivalence, we can consider a vector space isomorphism between these two equivalent divisors by multiplying the functions in L of G1 by Z. So that means algebraic geometric code, which is defined by G1, will be spanned by these vectors over FQ, and algebraic geometric code, which is defined by G2, will be spanned by evaluations of these functions in this Riemann space. So indeed, since we have observed that these the functions that has positive evaluations, or if we follow this notation, this shows the existence of such a vector, and indeed this shows us these two algebraic geometric codes are equivalent with respect to the definition of equivalence for algebraic codes. And for part B, conversely, we will see that if we consider a linear code C, which is equivalent to an algebraic geometric code, which is defined by a divisor G and evaluation of its Riemann space if given this Pi's. Then for this, the vector which defines the equivalence for each coordinates for given each these non-zero entries, we can consider them as non-transcendental functions. We can consider them as constant functions. So on the other hand, we are also given indistinct places. This allows us to apply the weak approximation theorem, which guarantees the existence of a function, non-zero function, such that z minus ai's has strictly positive valuations at pi's. So that means z minus ai is in pi. So that means z minus pi is ai, and since ai are non-zero constants, and from the beginning of the theory of the algebraic function, because we know that the constant field has trivial intersection with each place. So indeed, this shows us the evaluations of functions z at pi's are nothing but these non-zero constants ai's. And now, with respect to this function, with respect to this choice, if we set a divisor g prime, which is obviously equivalent to g, that has disjoint support from D, because that means it has no zeros at P. That has no poles and zeros at Pi, because we define them as ZPI. And indeed, we can also see that there's a vector space isomorphism between the Riemann Roch spaces. And if you consider the definitions of the algebraic geometric code, which is defined by G and G prime, with this choice G, we can see that indeed the code C is defined by